As promised, it is time for the infamous binomial probability distribution. This is a big deal. This is a big probability distribution. It's going to solve some problems for us and create some others. So let's remind ourselves what kind of problem this is going to solve. So remember our exploratory example from 6.1 where we had an NBA players that have a 77% chance shooting. That's actually an overall percentage for the NBA, and that's pretty much what most players in the NBA are like, Shaquille O'Neal notwithstanding. So you're going to randomly select 3 NBA players, have them shoot. We made a tree diagram, we found the probabilities, and all this mess. Now, notice that many of the probabilities repeat in that table. So if you look here, you can see the 0.0407 right there, and then another 0.0407 and another one right there. See them? Right, those were the ones that had 1 success and 2 failures. So what I could do is, instead of writing it this way with 8 separate outcomes, I could write the number of successful free throws. Remember, we learned that technique, changing it from individual recordings, if you will, to just the vast number of them. You know, there was 1 success, there was 2 successes, and so on. We learned that way back in section 5.1, I believe. All right, so this is the same table. I know it doesn't seem like it, but it is. You could have 0 successes. That's right down here, right? 0.012. You could have 1 success, and I highlighted that one in yellow so you could see it. 1 success was fail, fail, success, fail, success, fail, and success, fail, fail. It was these 3 that I highlighted in yellow right there. See them? Or you could have 2 successes. Okay, well, let me do green right here. That would be this FSS or these 2. And if you add up those 3, 0.136, 0.136, 0.136, you get 0.409. You with me? And then 3 successes means you had success, success, success. So the table, I'm going to do all this in color. Let's do red for no success. That's kind of sucky. So let's make that one red. So that's where that one comes from. Then these are all yellow. Right? And then green, and then the white one here, I'll just have to give it a color. Let's make it blue. There we go. Make it blue. If you have highlighters, you can highlight. You with? Everybody all right? So what you're doing is you're double checking for yourself how this works, right? So you're saying, okay, instead of breaking it down individually, I'm going to kind of group things together. All right, now we are going to figure out a way to make this work for us, because doing this longhand like this with this big table, that was annoying for 3 players, but it would be unbelievably hard with 30 players or 200 players or however many players the NBA has. It'd just be ridiculous. So we're going to have a formula, and it's going to come up with the bottom table for us. It doesn't do the top table, it does the bottom table. But that's okay. I mean, you can see that the bottom table really has all the components of the top table anyway. I mean, it's just slightly different. And the cool thing is that the formula we use is really simple to use, whether you have 300 players or 3,000 players. It won't make any difference. The table will work no matter what. Of course, with 3,000 players, you're going to have issues still, but at least you wouldn't have the, hey, I got to make a tree diagram for the rest of my life kind of issues, because that's how long it would take. I mean, it'd be ridiculous. All right, so before we get into that, first thing we got to do is we got to learn what a binomial experiment is, because the formula we're going to learn only works for binomial experiments. Now, binomial experiment is an experiment that has a fixed number of trials, right? Every repetition of the experiment is called a trial and has a fixed number. Those trials are independent of each other, right? So the first trial doesn't have any effect on the second trial, and so on. For each trial, there are only 2 mutually exclusive outcomes, success and failure. That's why it's called binomial, bi meaning 2, right? So you can succeed or you can fail, and the words success and failure don't have any meaning. It's not like, for example, a classic one of these is kids. You know, I'm going to have 3 kids. 3 kids, that's the fixed number of trials. They're independent of each other, because just because I have a boy first doesn't mean I'm going to have a boy second, right? And there's 2 mutually exclusive outcomes, success, failure, boy, girl, or if you like, girl, boy. It doesn't really make any difference which one you choose to call success. And the probability of success is the same for each trial of the experiment. In case of boys, girls, for most people, it's 50-50. Now, of course, it's not always 50-50, but for gender ones, it would be. And I cannot stress this enough. This is a really, really big deal. This is a very important concept, what we're looking at here, because this is how polls and surveys get broken down for us in statistics. We think of it, let me think. Oh, President Obama. So he's the president right now as I make this video. So you can say, do you approve or not approve of President Obama's job in office or something like that? And so you could say, okay, I'm going to poll 1,000 people. There's my fixed number, 1,000 people. Whether one person likes Obama has no bearing on the next person liking Obama, because we assume we're only polling 1,000 people out of the millions of people in America, that they're independent of each other, right? For each trial, there are two outcomes. Either you say, yes, I approve of Obama's job so far in office, or I do not approve, failure, right? And the probability of success is the same for every person. It's whatever it is, the mood of the country, right? So if, I don't know, if 52% approve of President Obama at this point in time, then you expect that probability of success to be 0.52 for every single person, right? All right. That means that every poll, every survey, well, not everyone, but a lot of them get broken down into yes, no. I mean, even if you said, yes, I approve of Obama, no, I don't, and I'm not decided, what you do is you take the no's and not decided and lump them all together and call those failure. And then the success is just the approval, right? Or if you're doing candidate A, candidate B, and candidate C, you say, well, if I'm interested in candidate A, then a vote for him is success, and the vote for the other two guys, that's failure, right? Okay, and then the rules then that we're going to learn for these probabilities, this is how later chapters polls and surveys are going to work. So big, big, big deal. All right, so let's look at our free throw thing again. So you say, okay, I have an NBA player, or free throw for any NBA player, to be honest, it's any NBA player, is 77%, which is the chances they're going to shoot a successful free throw. I got that numbers, I believe, from NBA.com. But anyway, so you're going to randomly select 3 NBA players and have each of them shoot a free throw. Explain how this experiment is binomial. So it's performed 3 times, no more, no less. It's fixed, right? Each one of them shoots a shot. There's 3 players. The trials are independent of each other. Now, I got to be honest, it actually doesn't matter whether you think of this for an NBA player. It doesn't matter whether you think 3 separate NBA players or 1 NBA player shooting 3 times. They've done several studies, and professional players who shoot so many free throws, they tend to be independent, just because they're so used to doing this as their job, that free throws, whether they make it or don't make it, doesn't really have a lot of bearing on their next time. And then there's 2 outcomes. They either make it or they miss it, right? Success would be they make it. Failure would be they miss it, right? Although if you're in the opposing team, I suppose you want the opposite, right? Missing would be success for you. But we'll just assume that we want them to make it, so that's success. And then the probability of success is 0.77 every time. NBA players are actually quite consistent in their free throw percentages. They just don't vary that much, either from person to person or over time. Now, there are some players that are exceptions to that, and generally as players age, they might get worse at free throws or something like that. All right, so that's a binomial experiment. It satisfies all the properties. So it's binomial because it satisfies, or the experiment, I should say, all 4 properties of a binomial experiment. And that's what I just showed. Now, there's some notation we have to learn. The fixed number of trials, that's called n, number of trials n. Then little p is the probability of success. And then 1 minus p, which a lot of books call q. Little q, get it? P and q. P, mind your p's and q's, huh? That's called the probability of failure. So that's 1 minus p because they're complements of each other. You either succeed or you fail, so they got to add up to 1. And then X is the number of successes in n independent trials. So you can get as low as 0. You can't have negative amounts of success, right? So you can get as low as 0, or you can go up to n itself and have, 3 successes or something. So if we look at our NBA players, for example, n was 3 because there were 3 of them. The probability of success was 0.77 for each one of them, so 0.77. Then the probability of failure is 1 minus 0.77, which is 0.23. And then my successes, I could go 0 success, but I could get 1 success, 2 success, 3 successes, which is what we saw right back here. Right? You could have no successful ones, 1, 2, 3, and so on. That's as high as you can get, right? Because you can't go any higher than 3 because you only shot it 3 times. If you shot it 10 times, then it'd be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay, now let's take a look at the next page. We need to determine whether the following examples are binomial experiments. If they are, we've got to assign them NP, X, and 1 minus P. So we flip a fair coin 3 times and record the number of heads. Okay, that's binomial. You're doing it 3 times, so n is 3. Your chances of success is 0.5, but that's also your chance of failure, 1 minus P, because 1 minus 0.5 is 0.5. X is the number of successes you could get. You could have 0 heads, that's 0. You could have 1, 2, up to 3. You can't get any more than 3 because you're only tossing it 3 times. All right, what about the second one? We have a loaded die. It tosses 5s 80% of the time. So we're going to toss the die 4 times and record the number of 5s. Okay, so this is binomial. N is 4. The chances of success it's rigged, right? It's a loaded die, but it still tosses 5s 80% of the time. So your chances of a 5 is 80%, right? So if you will, that's your probability of 5. That's your chance of success. So we're making success equal to 5 because they said record the number of 5s. So 1 minus 0.8, right, is your chance of failure, 0.2. Okay. And then, well, how low could you go? You can get 0 5s. You could roll 1 5, 2 5, 3 5s, up to 4 5s. No more than that because we only rolled the die 4 times. All right, suppose we loaded that or roll that same loaded die. We toss the die and record the number of rolls it takes to obtain a 3. So how many times do you have to roll it? Well, that's not binomial because you could roll it 2 times. You could roll a 3 on the first time. You could roll a 3 on the 10th time. Who knows, right? So n is not fixed. You could, you and I both taking that die, we'll roll it different numbers of times to get a 3 to show up. All right, the National Institute of Mental Health reports that there is a 20% chance of an adult suffering from a psychiatric disorder. 4 randomly selected adult Americans are examined. So n is 4, because you're looking at 4 adults. The chances of them having a disorder is 0.2, which is the probability of success. Again, success doesn't mean like it's a good thing. It just means that you're getting what you were looking for, which in this case is a psychiatric disorder. 1 minus P is 0.8. That's the chances of failure, not having a psychiatric disorder. Again, success and failure don't really mean that much, and they just mean success in statistics terms, not in terms of life terms. Now, the lowest you could have is none of them have a psychiatric disorder. 1 could have it, 2 could have disorders, up till 4, all 4 of them, right? But you can't get any more than 4 because you've only got 4 patients to look at. All right, what about a jar containing 5 red marbles, 9 blue marbles, and 6 green marbles? You randomly select 3 marbles from the jar without replacement. Well, that's not binomial then, because without replacement means they're not independent, right? Your probability of success keeps changing. If you reach into the jar and grab a red marble, for example, then you're fundamentally changing how many marbles are left and how many of them are red, right? So the probability of success is changing all the time based on what you pulled out the last time. That is so not binomial, right? It's not independent. All right, 1/4 of a certain breed of bunny rabbits have long hair. What is the probability that in a litter of bunnies, exactly 3 will have long hair? And this is not binomial because you have no idea how many bunnies are in this litter. How big is a litter exactly? Now, if I had said, what is the probability that in a litter of 10 bunnies? Well, then you'd know n is 10, and then that'd be much better, right? But we don't know how big a litter is, so we have no n, so this can't be binomial. Oops. All right, done with that. See you for the next page and the next video.